Hi everyone, welcome back. Next up we have Vladimir Vesic and Andrija Jovanovic. They're doing a joint presentation on scaling ML-powered noise suppression in Microsoft Stream. Hi guys, how are you?
We're pretty good, thank you.
Yeah.
Okay, so noise suppression is a feature of Microsoft Stream that allows users to isolate speech from videos by removing noise, music, and other sounds. So in their talk, Vladimir and Andrija will explain how exactly this technology works. Guys, the floor is yours.
Thank you.
Thank you. All right, so in this talk, this will be a technical talk. We will go into the details of the engineering approach that we took to make the noise suppression service in Microsoft Stream scalable. Before we get into the feature itself, I want to spend a few seconds talking about Microsoft Stream itself. Probably some of you have used it, but probably the majority of you haven't. Microsoft Stream is Microsoft's enterprise video platform. And what that means is it's a video platform, so you can watch videos and you can upload videos and all the other nice stuff. But it has a bunch of other features that are specifically tailored for enterprise users and for corporate communications. And for our feature, we try to figure out what are the problems that users are having when using Microsoft Stream. And when we talked to our users, one of the things that came out was that these videos in a lot of cases are not professionally recorded, they're recorded without high-end equipment, and they're recorded by people who are just random people, not video professionals. So one of the things that repeats is that people are recording videos in noisy environments, and then viewers have a hard time actually listening and consuming the videos. So this is actually not a new problem. There are traditional technologies based on signal processing, various types of low-pass filters that can handle this. But when we explore these possibilities, it turns out that they were not good enough for all the types of noise that we needed to cover. Let me give you an example. If you are talking, if you're recording a video and there's air conditioning on, then these traditional technologies can remove that type of noise. But for example, if you're in a cafe or there's some chatter in the background or music in the background, then these types of approaches will not be able to remove the noise. In the past few years, there has been a plethora of deep learning approaches to this same problem. And the good news there is that these techniques actually allow us to reduce or completely remove all types of noise. So if there's music in the background, if there's anything that's not your voice, a human voice, they will be able to remove it. On the other hand, they are very computationally expensive in comparison to the traditional technologies. So the challenge is, what do we do and how do we actually ship that as a feature? So our goal here is to create a deep learning powered noise suppression experience that will work reliably for millions of people who are using Microsoft Streams to do their work. And spoiler alert, we did it. And Vladimir will show you a demo of how this looks like.
So open it up a touch. Don't want to open it up too much, because when I close it in, it'll actually splay out a bit wider. So I think that's about right. Just get all the water out before I close it in. Otherwise, once you close it in, it's stuck. So to close it in, I'm just going to sort of collar it in gradually.
All right, you can pause the video. So I hope that this went through the stream. You can see that when a video has noise suppression, there's a tiny button in the bottom right that says suppress noise. And when you click it, the video will switch from its normal audio track to a pre-processed audio track that has the noise removed and that we created. So this is how the feature works. And I hope that the difference in the level of noise was very obvious. And Vladimir will now tell you a few words about how this model was actually trained to accomplish that.
Okay, so on this conference, you probably saw a lot of examples on how models look like and work. Here we are going to just explain some really high level of how we did this for us. So first of all, we recorded clean speeches. So basically people talking to high quality microphones in like empty rooms. And then we recorded also noises. So those are like dog barking or car passing by or things like that. And then what we do is we combine these two in the time domain, and we do Fourier transformation to basically move this into the spectral domain. Once it's in the spectral domain, we then send it as an input to our model, and model should be able to figure out how to clean it up. Model then outputs a cleaned up like speech, and then we are comparing that speech with the clean speech which we already have, and we are calculating loss, and we're saying, come on, model, you can do that better. So this is like the highest possible level, and now Andrija will explain what's the infrastructure which is allowing us to basically host this, and what technologies are we using. Andrija?
Yeah, so this model was trained by our colleagues in the Microsoft Research office in Beijing, and they trained it and they developed the model itself using PyTorch, which you might be familiar with. I hope you're familiar with PyTorch. It's a state-of-the-art framework for developing deep learning models. However, as Vladimir has mentioned, it's not just about the neural network itself. In order to process this, we need to actually get the input video, to separate the audio stream, to transfer it using the Fourier transform into a spectrogram. Then we need to actually pad it and to form the input to actually conform to what the deep learning model expects, which also involves a bunch of these specific mathematical operations. And it turns out that the version of this pre-processing and post-processing steps developed in PyTorch and, okay, Python, I guess, is just not fast enough for use in production. So what we did here is that we exported the model into the ONNX or ONNX format. ONNX is basically an open source standard that is framework independent and that exports your model essentially as a graph. And then on the other side, you have ONNX runtimes in various other languages that you can use to actually do inference on CPUs or GPUs in whatever framework you like to use. And in our case, we decided to use the ONNX runtime for .NET, and we basically picked up the model, we took it into our .NET app, and then we rewrote all the pre-processing and post-processing steps in C#, which gave us an order of magnitude performance boost in these steps. And then, okay, we have something that actually does end-to-end inference reasonably quickly. And to reach massive scale, we decided to create a cloud microservice around it. And okay, we are Microsoft, and the Microsoft cloud provider is Microsoft Azure. I just want to mention that, all right, this is an internal Microsoft product, but what we did was built on open source technologies and publicly available technologies. There's no Microsoft secret sauce in there. So basically, any company can use this exact same stack that we used without any trouble. So let's actually dive a bit deeper into the architecture of what's actually happening within the service. From the outside, it looks super simple. You as the user have this link to a service, and then you give it a video and say, please enhance my audio. And then this magical cloud brain will bring you back your video, except with an additional audio track that has all the noise removed. But actually underneath this, there's a lot of complexity hiding. So when you go and ask the service to remove your noise, it doesn't do that immediately. Your request will actually be bounced around a set of small, stateless, even tinier services. And the first of them is just something we call a front door. It's a super simple ASP.NET app that will just authenticate your request to just verify that you're not trying to attack us, and it will do some basic validation. And then it will post the request to two places. It will post all of the info that it needs to process it to a database, and then it will post the request ID into a queue. Then on the other hand, we finally get to this brain part, and around that brain part is a service we call the worker, which is what we've explained on the previous slide, and it will read a message from the queue. It will go to the database to get all the request info, and it will then do the magic essentially. And this is actually still kind of a simplified picture because we have a couple of other services that do things such as making sure that we are compliant, that take care of telemetry, that take care of disaster recovery. We will not go into these details right now, although Vladimir will mention some of them later. I will mention just the exact technologies that we are using. So for the compute platform for these services, we use Azure Service Fabric. Service Fabric is Microsoft's microservice platform, and basically almost every big Microsoft product in the cloud runs on Service Fabric underneath. For the persistent data store, for the database, we use our Azure SQL DB, and for the queue itself, we use Azure Service Bus. So at this point, you may be asking yourself, okay, why do we need all this complexity with a bunch of these random services going around and pinging requests to each other? So I will now leave it to Vladimir to actually go one level even deeper and to explain how that allows us to scale and to be cost efficient.
Thank you, Andrija. So as Andrija mentioned, now we're going to dive a bit into these core concepts. First of these concepts is robustness. I'm just going to click through here to show you. So this is basically the diagram which you saw, which Andrija showed you earlier, but it also has this noise suppression client. Noise suppression client represents a library which you need to have on your machine in order to communicate with our service. So as we're explaining robustness here, the way we define robustness is a way for our service to overcome certain errors and glitches which it inherently has by being built on the cloud. We have categorized these kind of problems into three categories and three basically levels. And first level is the low level. It represents functional level. So if we're trying to emit a request or something and the network just fails for that second or two, we are going to have a problem if we don't have a way of overcoming these kind of transient errors. So in case of like network and component glitches, for example, maybe the queue is down for a millisecond, we are fixing these kind of problems by basically introducing this kind of retry mechanisms on each of our calls. Second level is this machine level, meaning that, okay, requests are working and functions are working correctly, but what happens if machine fails? So for example, this worker picks up some request and then the OS crashes, or even as Andrija said, our services are stateless, so even updating of our application is going to cancel our work there. So the way we are fixing this kind of problem is basically by retrying message processing, meaning that there is some intelligence in this queue which is able to figure out that some worker picked up some message and that message is not being processed, so that it releases this message to another worker, because behind this worker there is actually a set of workers. On each machine there is one worker. And additional level of robustness on machine level we achieve by having this cleanup service, meaning that this worker is working with customer content. It has its own cleanup mechanisms to basically delete from the disk customer content. But in case that fails, we cannot leave just customer content on this disk. So we have a separate service which is making sure that everything is being cleaned up from the worker machine. And in case it's not, it's firing an incident to our team to take a look. And on the third and the highest level, this is cluster level, it can happen that all of these components are independently working correctly. But for example, all cluster is configured badly and workers cannot access service bus, for example. This means that even though every component is healthy, the whole cluster and processing is not working. For this kind of scenarios, we are having this failover watchdog. Failover watchdog is yet another stateless service which is reading the database and trying to see if there are some requests which are not being processed. In case there are, then it should figure out, okay, this whole cluster is not healthy, and it should requeue the requests into the queue of the healthy cluster. And what allows us, basically the underpinning principle of all of this, which allows us to retry everything and potentially do some processing multiple times, is that we've intentionally built everything to be idempotent, meaning that in case that we do something twice, that will not be a problem, since everything will just work as it should. We are just going to lose some part of the work. Now let's talk about the availability and disaster recovery. We define availability as the ability for our service to receive requests. So even if everything is down, we're going to say that we are available if we are able to receive requests. And disaster recovery means that in case that like meteor hits the data center, the customer should not see that at all, since everything should be failed over to another data center. Now I'm going to expand upon this part here. So in order to achieve availability and this high-level disaster recovery, we have two geo-paired regions, and from the US, for the US region, it looks like this. So we have West US and East US, which are paired, and then when noise suppression client emits a request, it hits this traffic manager. Traffic manager is a, let's say, dumb Azure component, which just reroutes the requests into different locations, into different endpoints based on certain criteria. For us, these criteria are health and latency. So if cluster is healthy, if both clusters are healthy, it will send a request to the nearest cluster. There is this component called load balancer, which is then in charge of figuring out where further on that cluster should request go, exactly to what front door should it go. This kind of infrastructure allows us to have this disaster recovery, but this is not a granular disaster recovery, meaning that from the client standpoint, if anything completely fails in one cluster, client will just not be able to see that. So that's a great thing, and it allows us to have this disaster recovery. However, our costs are really affected by this kind of design. So Andrija will talk about it later, but we are trying to avoid having processing being done in different regions from where the video actually is. Okay, on this slide, we're going to talk about reliability and how we achieved more granular disaster recovery. And how we define reliability is once acknowledged, request needs to be processed. So if we said that if we receive a request, we need to process it no matter what happens. We are achieving this by having this database. So database is our source of truth, and there we are storing all of the information related to the requests. Even though this looks like one database, it is logically one database, but in behind this is actually two physical databases. And in case it fails over, it will just not lose its data, and front doors and other services looking at it will not see any difference. Then there is this queue, which does not have a persistent storage, meaning that both front doors again see it as one queue, though there are two queues. But however, if it fails over, it will lose all of its messages. Front doors know about this queue, and they're queuing their requests into different sub-queues, and workers are subscribing to those sub-queues and are picking up those messages and processing them. Once worker picks up a message, it then updates this, what we call a heartbeat, in the database, so that all requests which are being picked up and being worked on have this heartbeat like up to date. Then there's this component called failover watchdog, which I already mentioned, which is looking at this database and checking if heartbeats of all requests are being updated timely. And if they're not, then failover watchdog is checking if there is something wrong with for example, workers in one cluster, and then it's requeuing these requests which have heartbeat which is expired into the queue of the healthy cluster. What this kind of implementation allows us is to be able to fail over independently different things, and that the rest of the system continues functioning completely normally without any problem. Okay, here, so now about scaling. So since most of our components are pretty independent and not entangled and coupled with other components, it's pretty easy to just scale them separately, especially since database and queue are Azure components, which we are currently utilizing pretty lowly, so pretty low. So if we pay more, it's really easy to just scale it more. On the other side, regarding machines, it's also pretty easy to both scale them up and down manually or automatically. And since our service has around 50 nodes at maximum, so 50 machines at maximum in certain regions, the first limit which we see here that Service Fabric has, it is at around 1,000 nodes. With that in mind, I'm going to let Andrija explain further cost optimization techniques. Andrija?
Yeah, thank you. So Vladimir has explained in detail all of the engineering components that allowed us to scale reliably to huge numbers of users. But in the cloud, the flip side of having huge scale is that your costs can spiral out of control. So here, we actually did a lot of work to reduce our costs and to reduce our cloud bill. But I want to emphasize something that's not a particular piece of work, which is just the process of how we approach this. One of the first things we did while developing the feature was we built a model that estimates our costs and that estimates how much money we will pay for this. And that allowed us to do hypotheticals of what if we do this kind of architecture or this kind of architecture. And then when we decided on something, we would update the model and iterate again. And this sort of approach is really valuable because it allows you to avoid going into dead ends and spending a lot of time building something that's just going to be too expensive. I'm just going to mention a couple of concrete things that we did, so this is not completely abstract. So one thing that Vladimir has mentioned in passing is that it turns out that when you dig deep into your bill, if you process your data in the same region in Azure where it is stored, your bandwidth is free. But if you try to move it out to a different region, then you have to pay for it. And in a lot of situations, this might not be a big deal. But again, we are a specific app. Our inputs are videos. So we are in a position where we might have to pay a lot of cost to actually process the video. So one decision we made early on was to try to process every video in the data center where it is stored. And this is broken only in some very specific edge cases. So this kind of changed our architecture from a couple of big clusters to having lots of small clusters around the world that allow us to save on bandwidth, and also as kind of killing two birds with one stone. This also allows us to stay compliant with various data governance laws such as GDPR. Another thing I want to mention is how this workload is shaped. And as we've mentioned in the very beginning, Microsoft Stream is an enterprise service. So we get huge amounts of load during working hours, and then it's very quiet during the evenings and nights, and then it's completely quiet during the weekends. So when we look at the average of the load on our service, we get something like every hour we need to process 50 hours of video. And that doesn't sound too bad, but actually in the peak hours, we have easily an order of magnitude more workload. So how do you actually provision the capacity for that? If you just provision for the average, you run the risk of getting stuck and not being able to process the requests. And if you try to provision for your peak load, well, then you have a lot of unused capacity sitting around and wasting money. So what we did was we provisioned enough capacity for some medium type of load. And then we know that if there's a sudden peak, if there's a huge amount of requests, the fact that we are an offline processing system allows us to tell to some requests you will wait a little longer, and then pass on some of that load to quieter hours and improve our utilization of the service and reduce our costs. These are far from the only things we did to optimize our costs. So I'm not going to go into all the details. I just want to give a couple of examples here. All right. So this was kind of a detailed look at all of the constraints that we had to encounter and all of the decisions we had to make while scaling this feature. Kind of trying to summarize what are the main lessons here. So the first thing is this kind of approach is not something that would have been possible 10 years ago or maybe even 5 years ago. We have ML itself starting to improve, but for us, maybe even more importantly, the ML infrastructure in the cloud is continuously improving, and the ways to run your models from the frameworks to the cloud components are now much more mature than they used to be, and this is now something that's actually feasible. Another thing is that, on the other hand, you can't just trust your cloud provider to solve all your problems for you. And some of our problems were very specific, and we had to get our hands dirty to actually build something that made sense. So Vladimir has talked about our requirement to still keep the service running, even if one part of the world goes completely offline. This is something that you may or may not have as a requirement in your service. Another requirement is that videos are huge. So this is also something that distinguishes us from the majority of machine learning systems out there, because we now need to take care of bandwidth. But then on the other hand, we are an offline system, so we can allow some latency, we can allow ourselves to do retries and things like that. So having your approach tailored to the specific requirements that you have, and keeping your scaling requirements upfront and keeping your costs down is something that will pay off a lot. All right. Before we wrap up, we just want to spend a tiny bit of time talking about the future of this feature, and that will also potentially answer a couple of questions that we got. So the thing that we are working on right now is real-time noise suppression. So as we've mentioned in a couple of places, this approach that we have is a fundamentally offline approach where you give us your video, and then sometime later on we give you back your video with the noise removed. And there are various both technical and machine learning challenges that prevent us from doing real-time noise suppression right now. So to mention just a couple, currently the neural network requires some amount of audio as context, so we can't just do real time because we always have over a second of delay. And then on the other hand, just the computational cost is too high to do real-time noise suppression on anything but the most powerful machines. So here we have made a couple of advances with our friends in Microsoft Research that we hope will allow us to actually do this in real time. And then that unlocks noise suppression in other scenarios. So we hope that we will be able to bring noise suppression to other Microsoft products, not just Microsoft Stream. One product that's currently implementing noise suppression is Microsoft Teams. And this is not being done by the team in Serbia, but it should be ready relatively soon. And then we are trying to bring this to Microsoft SharePoint as well. And then when we have that, there are also a couple of advanced scenarios that are also unlocked by this real-time noise suppression, such as this thing that we call partial noise suppression, where if you can do this in real time, then maybe it doesn't have to be just an on-off switch. Maybe we can give you a slider where you can say, please remove the noise, but don't remove all of it. I need like something in the background so it doesn't sound completely sterile, and maybe you have some input into how exactly that would look like. So yeah, this is it for us today. Thank you all for attending the talk.